So when we talked about linear regression, we talked about r squared. R squared being the proportion of the variation in y that is explained by the x variables. In logistic regression, we don't really have the equivalent, or in LDA. So how can we see whether the data fits, the model fits the data well? So one thing is to look at the prediction of the zeros and the ones and then compare that to the real zeros and ones. And if you make a table, real zeros and ones against predicted zeros and ones, you can see how well the prediction is doing. The ones that are in the top left or bottom right of the table, they are the correct predictions, and the bottom left and top right are the incorrect predictions, and we can see which one is how high these values are. So a high proportion of correctly classified ones and zeros means a better predictor. This matrix is called the confusion matrix. And it's very handy to understand how your model is doing. You can simply produce the matrix and compare. Now, in addition to that, people have come up with different statistics to look at those numbers. They want one number for how well it fits, not a table of 4 numbers. So you can look at the percentage of the zeros that were correctly predicted, or the percentage of the ones that were correctly predicted, or the percentage of the ones that were predicted that were indeed correct, or the percentage of the zeros predictions that were indeed correct, and so forth. So people have come up with all kinds of measures and all kinds of names for these measures. On this slide you see sensitivity, specificity and precision, which are some of the more common ones, but there are quite a few different ones. Yeah. So prediction, for example, is the correctly predicted ones among all the predicted ones. So you have all these different ratios that you can calculate. If you go to Wikipedia, you will find at least 10 or 15 of them. So one problem with looking at the confusion matrix and calculate prediction, sensitivity, specificity and so forth is that it all depends on your decision criterion when to predict a 1 and when to predict a 0. You remember that we looked at 0.5, for example, where we say if there's a greater than 50% chance that something is a 1, we predict a 1, and if it's less, we predict a 0. But this is not always the best way to predict. Sometimes it might be worse or better to under or over predict. If I want to see the risk of a war breaking out and the risk increases to 10%, I might want to look at that particular case even though it's well below 50%. So if I made a prediction between states of the chance of a war breaking out, I would have a much lower decision threshold than 0.5. So it depends what you want to do. If I want to look at loans and I'm worried about customers defaulting and I'm going to refuse loans when the chances is a bit higher, maybe I don't want to be already at 0.5, maybe I want to take a little bit more risk and only chase them if it really gets to 0.7 or 0.8. So when we look at the specificity, precision and so forth, the numbers are going to change if we change the threshold value. So how do we now know what is a good predictor? So one thing that helps is the ROC curve, the receiver operating curve. So this shows you for all the possible threshold values between 0 and 1 how these criteria change. And you get a curve, a line, and the simple idea is that there is a 45% line, like the diagonal through the plot. That diagonal is the equivalent of flipping a coin. So that's a really fairly useless model, right? If I know nothing else and I need to predict a 1 or 0 and I just flip a coin to do so, that is not very informative. If your predictor, your model gets under the diagonal, it means it does even worse than just flipping a coin. It would be better to flip a coin than use your statistical model. So that's not great. So the further away above this diagonal the line, the ROC curve is from this diagonal, the better your model is predicting. So you want it to sort of be pushed in this top left corner of the curve. So in this graph you see them for the 4 models that we discussed. The linear probability model, the very naive, like using group means, the linear discriminant analysis, and logistic regression. And we plot ROC curves for the same fake data. And you will see that in this particular case they all work pretty similar, except the naive using group means. That really does not work so well. So that particular model, it's closer to the diagonal, it's under the other lines, is therefore predicting less well. So the more this curve is pushed into the top left corner of the graph, the better. So and if I say that the curve should be as far as possible in the top left corner, the better the prediction, then maybe I can just calculate the amount of space in the graph that is under the curve relative to the amount of space that's above the curve. And this is called the area under curve. So this area for the diagonal line would be 0.5. Half of the space in the plot is under the diagonal line and half of it is above. So 0.5 for the area under the curve is the equivalent to flipping a coin. If the line was perfectly in the top left corner, so you would have a straight line up to the top left corner and a straight line to the right, the total surface under the plot would be 1. That would be a perfect predictor. So we can always perfectly classify any observation, whatever threshold we take, given the data that we use. So in that case, the AUC, the area under curve, would be 1. So this measure AUC is between 0.5 and 1. 0.5 being a fairly useless model that is the equivalent to flipping a coin, and 1 being a model that perfectly predicts.